My name is Marco with my partner Alden in the making of this paper. In this study, we are testing these three of NLP models, which include BERT convolutional neural network, robustly optimized BERT pre-training approach, trans-bidirectional LSTM, to find out which is the most accurate model with maximum accuracy with minimum computation. Also, trade off its strength and weaknesses of each model. With the best model, we will solve the main problem, that is efficiency of NLP model for business decision and the- identify certain tasks. So, I would like to discuss these three models one by one. The first model will be RoBERTa. It is a optimized version of BERT that improves BERT in training with more data, long sequences, also offering contextual understanding. But it also have its limitations that is expensive in terms of resources needs. Moving on to BERT convolutional neural network. It is a combination of BERT and, of course, convolutional neural network, aiming to balance accuracy and efficiency. Although BERT convolutional neural network still face some challenges in terms of convolutional optimization. Last model will be TRANS-BLSTM. It integrates transformer model with bidirectional LSTM to better capture long dependencies such as sequential data and complex data. But this also causes higher computational demands. Moving on to methodology. So, in order to achieve the best efficient model, we select several datasets for our model training. Each model will train around 70,000 data of sentence and recognize each sentiments. We take all data such as training loss, validation loss, all calculation that could be that like F1 score to determine the best model out of three model we tested.
Next, I will explain the results and output that we obtained from each model in our experiment. To preface and give the context of our implementation, BERT-CNN and TRANS-BLSTM was initialized with BERT-based uncased without any additional weights, and is then modified based on its respective architecture implementations. Meanwhile, RoBERTa was already initialized with pre-trained weights, which was then further trained with our dataset. From the graph shown in the experiment subsection, it displays the training and validation loss throughout the training process. A common motive shown on all models is an initial decrease up to the 6,000 steps. This is due to the models adjusting its weight significantly based on the loss gradients. This is then followed by a sudden increase, which might indicate that the models are overfitting. We can hypothesize the cause of this from a high learning rate and an unoptimal regularization, which is causing the model to overshoot its optimal weights. This could also happen because of the given dataset. So in future experiments, we can try adjusting those parameters to improve the training and validation loss. Let's now review the results from our model testing. Firstly, we observe a significant number of false predictions within the neutral sentiment category compared to the total instances in this class. On the other hand, there is a notable amount of true predictions within the positive sentiment category, especially when considering the total of number of instances in this class. In this case, we can hypothesize the cause being the skewed dataset, where the amount of positive sentiments outweighs other classes by a huge margin. It's important to note that the approach of this study is to keep things agnostic, which applies to the dataset, though this could be improved by having a balanced distribution in the dataset. Our result shows that BERT-CNN came in last with an F1 score of 0.7473, RoBERTa in second with an F1 score of 0.7627, and TRANS-BLSTM coming in first with an F1 score of 0.7648. From the data shown above, we can form a conclusion. RoBERTa generally outperforms BERT-CNN in every class, particularly it has better recall and precision. This performance increase might originate from the extensive pre-training from the book corpus with a vocabulary class of 30,000, and the transformer architecture allowing it to perform better in understanding nuanced sentiments. BERT-CNN shows the lowest performance out of the three, since this architecture uses the BERT model to predict features, which is then classified by the CNN layer. This might be less effective at capturing long-range dependencies. This hypothesis is backed by the model having the lowest performance on the neutral sentiments where the nuances are heavy. Lastly, TRANS-BLSTM shows the best performance among three. It balances out the precision and recall effectively and has the highest true positive rates with lower false negatives. The architecture of this model makes it effective since the transformer components captures the global context and the LSTM components is effective at sequential dependencies. From this, we can conclude that it's important to select the appropriate model architecture based on specific application requirements. The choice of the model significantly impacts the accuracy and the reliability, which is crucial in business decision making and other areas where understanding human emotions are vital. In these models, exploring other hybrid approaches, training with a broader and more balanced dataset, and ensuring model fairness and robustness to increase effectiveness in the implementation of sentiment analysis technologies. That concludes our paper. Thank you for listening.